Hi, my name is Ian and I'll be presenting on my FYP, Building a Compiler. So first, the objective of this project is to build a compiler that can translate the source program of a high-level language to JVM bytecode. So the high-level language can support common control structures like if statements and while loops, multiple functions, and multiple data types such as integers and floats. So this is an overview of the CZEC 3007 compiler techniques module offered here at SCSE. To aid students in their learning experience, we want to individually convey the complex technicalities behind each phase of a compiler which corresponds to a topic. So for example, in Lab 1, students can examine the source code of this project and understand how lexical analysis is performed. In Lab 2, students can examine the source code and see how syntax analysis is performed, and so on. So now we'll be moving on to the development of the project. For Lab 1, we are using a technology called JFlex to write specifications and generate a lexer. So in the specifications, we can use regular expressions as seen from this example. So over here, we are defining a regular expression for float literals, and a float can be one or many digits followed by a dot, followed by one or many digits, followed by an optional small f or big F. So here are some test cases that were written to ensure that float literals are recognized correctly. In the high-level language, we allow trailing numbers and leading trailing zeros. So we want to check for that. We also want to check that the float literals can also be recognized correctly when the positive and negative signs are appended to them. So the expected output for all these test cases are pass. Here are some more test cases that should pass. So over here, in this first example, we are checking for the small f and big F. And in the next example, we are checking that the float keyword is recognized correctly. These are some additional tests to ensure that incorrect floats are not recognized as float literals. For example, if a float is missing the integer part, it should not be recognized as a float. Likewise, if the fraction part is missing, it should also be not recognized as a float. Lastly, if there is a typo, for example, if there are two dots included, then it should not be recognized as a float as well. Next, in syntax analysis for Lab 2, we are using a technology called Beaver to write specifications to generate a parser. Some semantic actions are also included to support the building of the abstract syntax tree later on. For example, in a Boolean literal, there are two possible values, true and false. So we can see that the context-free grammar is simply Boolean equals true or false. And we also specify the semantic actions here so that we can build the AST. This is an easy example. The next one is more complicated. This one shows the context-free grammar for arithmetic expressions, which include addition, subtraction, multiplication, division, and modulo. So here are some tests to test for the syntax correctness. So the expected output for all these tests are pass since they do not violate any syntax. Next is semantic analysis in Lab 3. So over here we are using a technology called JustAdd to write grammar and attribute specifications to generate AST classes. So for example, this is some extract grammar that is used to define the AST classes. For Labs 3 and 4, an abstract syntax tree is required. So this AST serves as an intermediate representation of the source program and is used for post-parsing processes like semantic checking and code generation, which are Lab 3 and Lab 4 respectively. So this AST captures the structure of the source program and it omits unnecessary syntactic details. An example is as follows. So in Lab 3, here are some tests to check for the scope and the type. So these are some tests that should pass as there are no scope or type violations. For this first test, since there are no scope or type mismatches, the test should pass. However, for the second test, we can see that a previously defined variable is redefined again with a different type, and hence this test should fail. Next, this is a test that checks for type mismatch between the elements in the multidimensional array. So for example, since a Boolean array is assigned to an integer array, the test should fail. Here are a few more tests that test for the same kind of type mismatches within a multidimensional array. Next, we convey the technicalities behind a code generator in Lab 4. So here we are using a visitor pattern to visit AST nodes and generate code. So this has to be implemented in the previously generated AST classes. For example, in binary expression.java, an accept method has to be included. So this file called expressioncodegenerator.java is using a technology called suit to generate code for expressions. So for example, over here for an assignment expression, we need to check if the left hand side and right hand side are of different types. If so, we want to cast the right hand side to the type of the left hand side. And the following are suit code that are used to achieve this. Another example is the parsing of binary expressions. So for example, there are two possible cases. The left hand side is of an integer while the right hand side is of float. So in this case, we want to cast the weaker type to the stronger type. So we want to cast the left hand side to a float. Likewise, if the opposite is true, where the left hand side is of float type while the right hand side is of int, we want to cast the right hand side to a float. That is the end of my presentation. Thank you.